Okay, so now the recording is underway. We're going to talk about magnetism. Let me pull up some slides. Okay, do you guys see magnetism?
Yep.
Kelly, you have to answer my questions and read the chat for me.
No problem.
Thank you. All right, so let's get underway. Magnetism. So magnetic fields. So just like electric fields, so remember electric field, every point has associated with it an electric field. Excuse me, an electric field vector. I should say every point in space has associated with it a vector, which is the E vector. And when you put a charge there, then you get a force. So that's what the word field means. Field is a mathematical word that means mathematical word that means that a point in space has a vector associated with it. So we're going to have magnetic fields. So points in space will have a magnetic field vector associated with it. And where do magnetic fields come from? So I'll give you a couple answers. Maybe the most obvious one is they come from magnets. So here is a magnet. There's a magnet. And as you probably know, we have, the ends are different because if you have two magnets, I'm sure you've played with magnets before, they'll push apart from each other if you orient them a certain way, and they'll stick to each other if you orient them a different way. So there are differences in the ends to them, and we call one end north and the other end south. And these in blue lines are these magnetic field lines. This is what I said. Magnets have a north and a south pole. Like poles repel, and opposite poles attract. So if you try to push two north poles together, they won't like it. They'll repel each other. But a north and a south pole will stick together. So interestingly, you always find a north and a south pole together. Nobody has ever found a magnetic monopole, meaning an object that only is a north pole or an object that is only a south pole. And people have tried very hard to find such a thing. But we've never found any evidence that such a thing exists. So what that means in terms of the magnetic field lines is that you have closed circles like this, or closed, not necessarily circles, closed loops. Right? So you see on the outside, there's this magnetic field line, and then it goes on the inside and continues, and then it goes back out. Electric fields, remember, we do have electric monopoles. Those are positive and negative charges. And you'll remember that the electric fields begin and end on charges. And because we have no magnetic monopoles, then the magnetic fields are always in loops. Magnetic field lines, I should say. Okay, so the field lines point from the north to the south, as you can see on the outside there, outside of the magnet. The direction of the magnetic field lines is given by, if you can imagine, putting a little tiny compass there and seeing which way the north would point. So outside of the magnet, the compass would point towards the south pole of it. The north pole of the compass would be attracted to the south pole of the magnet. Okay, and field lines, as I said, form closed loops. I said this, unlike electric fields. Okay, and remember what field lines are. Field lines tell you, or rather, the magnetic field itself is tangent to the field lines at any given point. That was true for electric field lines as well. So for example, if I want to know what the magnetic field at this point is, the vector is actually tangent to the blue magnetic field line at that point. So they look like this. These yellow vectors are the magnetic fields at these locations, here, here, and here. Drew a couple extra, okay. And the same down here, right? Excuse me. Okay, here's a fun fact. The geographic north pole of the Earth is actually the magnetic south pole of the Earth. And that is why the north end of a compass points to geographic north, I should say. And so here is the Earth. And think of the Earth as a giant magnet oriented in this way, with the south pole of the magnet at the north geographic pole. Right, so that's why, if you're over here, and it looks like if you're in Hawaii and you have a compass, the north pole of the compass, the darker end of the magnet itself, ends up pointing towards the south end of the Earth magnetic field. So that's kind of a curious thing.
Why wouldn't we just change our convention to match it? To establish.
Well, it would be, it would. You mean call the geographic?
Yeah,
north
geographic pole, the South Pole, and the North Pole, and just literally like invert. It doesn't matter. I was just curious.
So then we would have to reverse the letters on the compass. Yeah.
Yes.
At any rate, this is what it is. Maybe it's because these things were discovered and defined before we knew what the direction of the magnetic field of the Earth was. I'm not sure. Okay, magnetic fields, where do they come from? Here's a second answer. Moving charges. If you have a charged particle that moves, you have a magnetic field. So in particular, if you have current carried by a wire, like this, you create magnetic fields around the wire. Or you don't, it just happens. You always say this in a kind of temporal way, like the current happens and then the magnetic field occurs, but it's really kind of simultaneously. They happen together. It's not that one causes the other, although sometimes it's helpful to think of it that way. So here's a wire, and it's in the plane of the screen, and these blue magnetic field lines are supposed to be perpendicular to the screen, right? So this is kind of a perspective drawing. Do you guys see me, by the way?
In the bottom right-hand corner, I do.
Yeah, so you can pull up an image of me. So
yeah.
If necessary, I can have my little, I don't know if you can see me, but I have an arrow. You see my arrow?
Yes.
And then I have a hoop.
Yes.
So what's on the screen is depicting this idea. It's in 3 dimensions. So don't get confused. Those are actually circles, they're not ovals. And the circles are perpendicular to the screen. Right, so I just want to emphasize that point, make sure no one's confused about that. Okay, and now we introduce a right-hand rule in order to tell us what the direction of a magnetic field is, given that there's a current going in a certain direction in a wire. I'm going to call this right-hand rule number 1, RHR number 1. And the idea is this. Imagine taking your right hand and grabbing the wire in such a way that your thumb points in the direction to the current, in the current. Points in the same direction as the current. All right, so I encourage you out there in your homes, take a pen or a stick or something like that and imagine, here's my arrow and it's pointing upwards. I take my right hand and I'll grab it like this with my thumb in the direction of the current. You'll see that your fingers wrap around the stick or the wire in a particular direction, and that gives you the direction of the magnetic field, as you can see here. If the current were going the other way, you'd grab the wire with your thumb pointing downwards, turn my arrow over, and then the magnetic fields would go the other way. Is that clear? So this is a little frustrating because when I do this in person, I can actually see everybody, put their right hand up in the air, and I can harass the people who refuse to participate. But I can't see any of you.
Yes, it makes sense.
So yeah, if there's anything ambiguous, you've got to stop me sooner rather than later, so that I can demonstrate and make sure you understand this in 3 dimensions. Okay, was that a question?
I like your props. Kirsten likes your prop. Your arrow.
Oh, okay. So I'm glad you can see it. Yeah.
Yes.
What's the next one?
Julia says, yeah, me too. He needs to just practice more problems using the right-hand rule. I did use my pen, just so you know. I followed you.
Yes, very good. And by the way, make sure you use your right hand.
That's actually my problem because I'm left-handed, so I always do everything left.
Yeah, be very aware of that. And those of you who are left-handed have the
disadvantage?
The advantage that when you're writing, you can write with your left hand and do the right-hand rule with your right hand. Those of us who are right-handed have to put the pen down, wave your hand in the air to apply the right-hand rule, and then pick up the pen and write down whatever it is you figured out. Don't be lazy and just by mistake use your left hand, because you'll get everything backwards. And for that matter, don't use your left hand with the understanding that you're just going to reverse everything, because that will get confusing and ambiguous. I guarantee it. Stick to your right hand.
That is a good point, because I probably would have tried to just think it would be reversed.
And again, when I'm in front of people and I actually see them, I always make the joke where I point to somebody who's doing it wrong and say, no, your other right hand. But I'm deprived of that opportunity this time. Okay, the letter B is used to denote the magnetic field. And so you can see here's the B vector with a little arrow over it. So this, I didn't write them. So this little yellow thing is the magnetic field B at that location. And as I said, those magnetic fields are tangent to the magnetic field lines. So all these yellow vectors are different versions of B. So, B1, B2, B3, B4, they're different vectors because obviously they point in different directions, as you can see. So I didn't label them B because I didn't type in all the subscripts. But this is B1, B2, B3, B4, B5, B6, B7, B8. B is your magnetic field. You might come across H. The H has a slightly different meaning, but I don't think that's in this book.
I haven't seen it so far.
Okay. Okay. More comments about magnetic fields. So what can we say about the strength of magnetic? What is the magnitude of a magnetic field? Okay, so let's consider a distance r measured perpendicularly away from a straight wire, and ask. So here's the magnetic field vector, right? It's perpendicular to that circle. Excuse me. Tangent to that circle. I keep screwing that up. We can ask, what is the magnitude of that vector, that magnetic field vector B? The answer is this. Mu sub 0 I divided by 2 pi r. Mu sub 0 is this particular number, similar to big G or whatever. It's that specific number that tells you something about the nature of reality. I is the current carried in the wire in amperes, and r is that distance in meters. 2 pi is the number. Right, so that is the magnitude, and you can see, as you can see, the farther away you are from a wire, the smaller the magnetic field is. But not like gravity, where it's 1 over r squared. This is 1 over r. Here's a fact. If a current in a wire flows where there is a magnetic field, then there's a force on the wire that carries the current. That is just a fact that you can observe. The force depends on how the current is aligned with respect to the magnetic field. Here's a diagram from the book. So imagine that there is space in which the magnetic field points to the right. So you imagine the space in the plane of the screen has a magnetic field that points to the right, and also in front and in back. There's uniform magnetic field that points to the right. And here's a current carrying wire in gray of length L here. The length L is the length of the wire that's within the magnetic field. So that's why you see it starts from here and ends there. And it's oriented relative to the magnetic field at this angle theta. You have the current going towards the upper right here. Okay, you will notice if you do this experiment that you get the most force acting on the wire, the largest magnitude force, when this angle is 90 degrees. So if the current is perpendicular to the magnetic field, you'll get the most force. And you'll get the least force, actually zero force, if the angle is 0 or 180 degrees. If the current flows in the same direction as the magnetic field or opposite the direction of the magnetic field, there's no force on the wire at all. So that's a kind of curious thing, isn't it? Is there a question?
Yeah, so, sorry, I'm not a great reader. So that is when there is an applied magnetic field, or is it just naturally a current in the magnetic field?
Yeah, all I said is that there is a magnetic field. I didn't say where it came from.
Okay.
This is not the magnetic field that's generated by the current. This is a magnetic field that is just there. We can talk about, we've talked about where magnetic fields come from. There could be, magnets that create this magnetic field, or there could be some other thing, some other moving charges that are causing this magnetic field B, different from the current carried in the wire. But in this formulation, the magnetic field is just plain there, and then you stick this wire in its presence. Okay?
I believe so, but I'll let you know.
Yeah, well, this is just the way I'm setting it up. The magnetic field is there. You put the wire there, and it will feel this force. I'm just telling you, that's a fact. Most force occurs when the wire is perpendicular to the field, and zero force if it's parallel or anti-parallel to the field. Now, there's another right-hand rule. Right-hand rule number 2 will tell us the direction of that force that acts on that wire. So with the geometry that I have on the screen here, it turns out that the force is into the screen. And we'll go on to work that out and explain how to do this right-hand rule. So use right-hand rule number 2 to find the direction of that force. And here it is. So again, I would demonstrate this, but if I do it, you'll see it backwards. So I'm going to try to describe it. Magnetic field points to the right. It exists in the space in front and in back of the screen that you're looking at. And you have a wire in the plane of the screen carrying a current towards the upper right-hand corner. To apply right-hand rule number 2, you take your fingers and you point them in the direction of the current, with your hands stretched, flat like this. Put your fingers in the direction of the current. Now you see that there's some ambiguity in the way you can orient your hand. You could rotate your hand all the way around, and what you want to do to apply right-hand rule number 2 is to put your hand in such a way that the fingers point in the direction of the current, and you can bend your fingers towards the magnetic field. That's what's drawn on the screen there. So that hand has a thumb pointing into the screen, that's why you don't see it, and the closest finger that has that blue arrow B on it, that's the pinky. So put your hands in that configuration. Point your thumb to the screen. So like this. Actually, no, I should not do it because you're seeing an inverse image of me. I have to describe.
I was just going to say, I see your pinky.
Frustration with doing it on the screen.
What if you used your left hand? Then you could point the thumb.
No. Never, ever consider using a left hand.
Okay.
Trust me.
Kirsten said she doesn't.
Okay, so I will describe what to do.
Okay.
Given the situation on the screen, point your thumb directly at the screen. Point your fingers in the direction of the current towards the upper right-hand corner, and you will see that you can bend your fingers towards the right, towards the magnetic field. So in that orientation, the thumb of your hand tells you the direction that the force is.
Okay.
Okay. Was there something in the chat?
Just that we don't think our fingers bend this way, but we're good.
They will if you orient your hand correctly. So remember, what's on the screen is point your thumb towards the screen.
So the force is going into the screen.
The force is into the screen in this case, yes. I wish I could demonstrate it for you, but I can't really.
That's okay.
Because you will see an inverse image, and that's confusing, right? If I point into the screen, I'm pointing at you, right? So that's
we are the force.
That's wrong. Actually, this is what I can do. It occurs to me. Let me make sure I see myself here. All right. So I can be in space. So do you guys see me? Hi, everybody.
Yes.
Okay, so I have my arrow here, and the sharp point of the arrow is this one. So that's a current that's going up here. So never mind the picture on the screen for the moment. Look at me instead. In fact, I'll do that. I'm going to stop sharing the screen so you can see me, and that way I can see myself bigger. Make sure I'm doing this right. Why can I not see myself bigger? I guess that's a zoom thing, not a...
You might have to change your view. So you can do like Earth node, or you can do whatever one's.
I only have 2 different views, and none of them have me looking big.
Oh, but you're big on my screen, if that helps.
Okay, so that's important. All right, so hello, everybody. Here's my arrow, and imagine the space around me. I have a magnetic field that points over there towards my right. I won't say that. Just the magnetic field points that way, the direction of my pen, that way. And here's the wire carrying the current with current going that way. I would do the right-hand rule like this. So here's my right-hand rule. My fingers go in the direction of the current. I go around and I orient my hand so that I can bend my fingers towards the magnetic field and point that way. Force is this way. And that's true, however I orient things. Okay, I hope I'm not confusing people. But let's go back to the slides now. Wait, I was going to see. Now that I'm here, I'll look at the chat. I guess some time ago, Kristen was asking, so is that when there is an applied magnetic field? Oh, that makes sense. Yeah. So
that was a question. Yeah. I think we're good.
It was just the way I was setting it up. The magnetic field is just plain there. Where's my PowerPoint? Here we go. Okay. Okay, so this is where we were. Let's now go on. Okay, so that right-hand rule number 2 tells you the direction of the force. What is the magnitude? Here is the magnitude. It's given by this formula. Current times the length of the wire that's in the presence of the magnetic field. As you can see, that's the L here. They call it 12 centimeters. The strength of the magnetic field, B, and then sine of this angle, theta. So this sine of the angle is what makes the force maximal when the wire is perpendicular at 90 degrees to the magnetic field and 0 when it's in the same direction. Here I've listed what the symbols mean. Interestingly, this is what actually defines the magnetic field, the B. So we can take this equation and solve it for B. And it looks like this. And so that'll tell us what the units for B are. So the units are Tesla, after the famous scientist. And a Tesla is given in terms of other units by this formula. So force is in newtons, current is in amperes, and L is in meters. So 1 Newton per ampere meter is a Tesla. Tesla is a pretty big unit. 1 Tesla is equal to 10,000 Gauss, another unit of magnetic field. And the Earth's magnetic field at the surface is about half of a Gauss. So you can see that a Tesla is significantly stronger than the magnetic field of the Earth. MRI machines, a standard typical MRI machine has a big old magnet in it of about 3 Tesla. And some of the more accurate ones, they're becoming more common, have 5 Tesla magnets. If you're in the presence of a 3 or a 5 Tesla magnet, you have to make sure not to have anything metal around you. If you're carrying a screwdriver, it'll fly out of your hand. Metal chairs will get crushed. Actually, not quite. They will move. It's 5 and 10 Tesla when they start to fly around.
I remember they worked in a 1.5 Tesla, and it was, wow, expletive.
Yeah, you have to be careful. You have to not bring your credit cards, or they're going to get erased. Although now we have those chips, so maybe that's not applicable anymore. Okay, so Tesla is a big amount of magnetic field. All right, here's another fact. This is just true. If a particle with a charge plus q, so imagine a positively charged particle, if that particle moves with a velocity v, it's a vector, through a region where there is a uniform magnetic field B, then it will experience a force. So again, in this case, I have a picture. Here's a picture in the book. I heard a ding. Is there a question in the chat?
Not at all, just comment.
Okay. What's the comment?
I said so no piercings then.
Oh, yeah, because it'll rip it out of your ear. That's right. Okay, so this diagram has been confusing to people in the past. So this pink thing on the left is a magnet. There's the north end. On the right is a other magnet oriented with the south pole. So they would ordinarily attract each other, but they've been fixed in space. And we have this magnetic field in between. This particle, this is the red particle that has positive charge. Here's its velocity vector. It is moving, but it is not moving in the plane of the screen. So it's not moving towards the lower left. It's supposed to be a perspective drawing, and the particle is actually coming out of the screen. And so this is important to realize about this diagram. Magnetic field is to the right, in the plane of the screen and in front of the screen and behind the screen, always pointing to the right. And the particle is coming out of the screen. So to find the direction of the force experienced by this particle, it's the same right-hand rule that I just told you, which kind of makes sense because if you have a positive charge moving in a certain direction, you have a current in that same direction. So it's the same idea, except we don't have a wire, a physical wire. Instead, we just have the moving current. But okay, so the force experienced by a charged particle, positively charged particle that comes out of the screen with the magnetic field oriented as shown, will experience a force in the upward direction. So this one is a little awkward to do with your hand. But what you can do is, if you're looking at me, sort of like point to your chest like this. So you have your hand oriented like that. And if you do that, then you'll see that your fingers point in the direction of the current out of the screen, right? And you can orient your hand back and forth so that the palm of your hand points towards the south, which allows you to then bend your fingers in the direction of the magnetic field. And you'll see that the force points upwards.
And the force.
What I'm doing at the end of my screen is this. So you should have your hand like this, pointing towards your chest, and then hold it in front of the screen, and then you can see. What was that, Kelly?
The force is still your thumb.
Yeah, the thumb tells you the direction of the force. Can everybody understand that right-hand rule? Please ask now so that I can try to explain it.
I'm going to go
So again, don't look at my hand, but instead put your hand in the orientation where you're pointing at your chest. Actually, there's the diagram that goes with what's on the screen there.
And when you say south, you mean the pole of the magnet south, not the direction south.
You want to bend your fingers towards the B. See, the B points to the right. Magnetic field lines go to the south pole, which is why they're pointing to the right. So there's your right-hand rule. The fingers with a flat hand point in the direction of the current. Orient your hand so that you can bend your fingers towards the magnetic field. And then if you can do that, then the thumb gives you the direction of the force.
Why point it out chest? Because the particle current is coming out of the screen?
Yeah, imagine there's a positive charge coming out of the screen. That means there's a positive current. Excuse me, that means that the direction of the current is out of the screen. So your fingers should be oriented out of the screen.
Oh yeah, that diagram blows. That doesn't explain that. I can totally see why that would be confusing.
Yeah, it's a perspective thing. Yeah, so let's get rid of it. Yeah. Again, so put your hand up in the air and then bend your arm around like I'm doing and point it towards your chest. Do not look at my hand, look at your hand when you're doing that. So your fingers come out of the screen, oriented so your palm faces the right. That way you can bend your fingers towards the right and then the force points up.
So
is there something else in the back?
Yeah, if it were a negative charge, would it go toward the screen? Would it be in the opposite direction?
Funny you should ask. It's there. If a negative charge, then the current points in the opposite direction. If a negative charge comes out of the screen, as it's supposed to be depicted here, then you have a current that goes into the screen. That's right. And here I have it in words. To solve the situation that's on the screen right now, it's a negative charge coming out of the screen. Point your fingers into the screen, because that's the direction of the current. Orient your hand so that your palm faces towards the right. That way you can bend your fingers towards the magnetic field, and then you'll find that your thumb is pointing downwards. What's in the chat?
I would say, so the charge is still coming towards us.
Yeah, see, I wrote it here. The particle is coming out of the screen. In this case, it's a negatively charged particle.
But the current is going into the screen, so you're oriented.
Yeah, that means conventional current is into the screen.
Okay.
Okay, so let me back up, because I wanted to tell you that the magnitude of the force is given by this formula. So QVB sine of theta. Q is the charge on the particle. V is how fast it's going. And B is the magnitude of the magnetic field. The angle, theta, is the angle between the V vector and the magnetic field vector. The velocity vector and the magnetic field vector. Okay?
Can you demo the other one? Is it with a negative?
This one?
Yeah, because I must be doing it wrong.
So I'm reluctant to, because of the screen thing, but I have it written in words. To do this one with right-hand rule 2, point your fingers into the screen. Because remember, you have a negative charge coming out of the screen. That's a current that goes into the screen. So point your fingers towards the screen. Orient your palm so that it faces towards the right, because that's the direction of the magnetic field. In that way, then you can bend your fingers towards B, towards the magnetic field.
Gotcha.
And if you do that, you'll find that your hand is oriented so that
I failed in the palm.
your thumb is pointing down.
Okay.
So point to the screen and give it a thumbs down. That's the orientation of your hand. And not a commentary on my presentation.
No, never.
All right. I go on. So brief recap. So I like to give formulas with pictures so that you always associate the two. So you should have this in mind. Magnetic field given by current carrying wire is this picture and this formula. So right-hand rule number 1 gives you the direction of the magnetic field. There's the magnitude. This fact, a current carrying wire in the presence of magnetic field experiences a force. Use right-hand rule, it should say number 2, to find the direction of the force. And here's the magnitude of the force. Here's the meaning of the symbols. We went over all this. And then the third one is a particle that moves with a certain velocity through a magnetic field. It's the same right-hand rule as what we just did previously, because a moving charge is a current. But the formula is written in terms of the speed of the particle in this case. So charge times V. Okay, so you should know these things. You should know these 3 equations. You should know the right-hand rules, and you should know what situations these are applied to, what each of the symbols mean, and what the formulas tell you, which is what was on those previous 3 slides. So just a quick summary of that slide you can refer to later. All right, so let's apply this to a couple of situations. So it's interesting to think about what happens if you have 2 current carrying wires that are next to each other. So here's one current carrying wire, and you can see the magnetic field. It has this magnitude at a distance r away from it, measured perpendicularly from the wire. Suppose I put another wire in the same orientation, parallel wires with the currents going in the same direction. It has its own magnetic field like this. But what happens because they interact? So notice, I'm going to have them a distance r apart as I showed. Notice that because of the left wire, there's a magnetic field at the location of the right wire that points into the screen. Apply right-hand rule number 1 to the left wire. Imagine grabbing it, and then you'll see that if you grab that wire that's in the plane of the screen, at the location of the right wire, your fingers go into the screen. Does that make sense? In other words, in front of the screen, the magnetic field points to the right. Then it curves around and points into the screen at the location of the wire on the right. And behind the screen, it starts to turn to the left and then continues around. But what's important for me right now is that at the location of the right-hand wire, there's a magnetic field that points into the screen due to the presence of the left-hand wire. So we have a current-carrying wire. The left-hand wire is a current-carrying wire in the presence of a magnetic field. So we'll apply right-hand rule number 2. Put your fingers in the direction of the current. Orient your hand so that you can bend your fingers so that they point into the screen. So point the flat hand with fingers up. Bend your fingers so that they point into the screen. The thumb will tell you that the force experienced on the right-hand wire is to the left, as shown. Okay. Is there a question?
No, I just said, what do you know? It does.
Yeah, if you're using your right hand.
Challenge
Okay.
number 1.
So we just figured out the force that acts on the right-hand wire because of the left-hand wire. Right? The left-hand wire creates this magnetic field, and then we have the current carried in the magnetic field creating this wire, this force. But it works the other way around as well. By the way, here are the formulas for the magnitudes. So the other way around, the left-hand wire, the right-hand wire creates a magnetic field at the location of the left wire that points out of the screen. Imagine grabbing the wire on the right with your thumb pointing up. You'll find that to the left of that wire, your fingers would come out of the screen. So that is why at this location, there's a magnetic field coming out of the screen due to the current carrying wire that's on the right. And then once again, we have the left current carrying wire in the presence of the magnetic field generated by the right wire. So apply right-hand rule number 2 again in this situation. So again, flat hand with the fingers pointing upwards, and then orient your hand so that the palm faces outwards. So that way you can bend your fingers so that the fingers then point out of the screen. Start with your fingers, flat hand, fingers pointing up. Bend your fingers, oriented so that you can bend your fingers so that they point out of the screen. And then you'll find that the right-hand rule is telling you that there's a force on the left wire that points to the right. Can everybody do that?
I understand the first right-hand rule applied to this, but I'm kind of confused by the second. Is it facing up because of the direction of the current?
So the first right-hand rule tells you the direction of the magnetic fields. That was okay?
Yes.
So at this location where I'm pointing, the location at the presence of, at where the left-hand wire is, there's a magnetic field that points out. That's generated by the right-hand field. It's not drawn, but the right-hand wire has a current going up. So you grab it with your right hand, and you'll see that on the left of it, the magnetic field points out. Your fingers come out of the screen. So then there's a magnetic field that points out. There's a current that goes up. Right-hand rule number 2 tells you to point your fingers with a flat hand upwards. Spin your hand around so that you can bend your fingers so that they point out of the screen. If you do that, you'll find that the force, your thumb points in the direction to the right, telling you the force is to the right.
Okay, we gotcha.
I hear lots of dings, so I'm just going to go and look at what's on the screen, what's in the chat. Yes, the images are confusing. So the chart, oh no, that was the previous diagram, yeah. Oh, this is what you just told me. Oh, okay, so I didn't miss anything in the chat.
Yeah, you told me to read them, so I have been.
Yeah, okay. I just heard lots of dings, and so I thought that maybe that
I'm failing my job?
there were just too many for you to keep up with.
No.
But okay, so once you've gone through this little exercise, you find that the wires attract each other. They experience forces towards each other. And in fact, you can do this. If you're doing the lab, I'm sure you do this. You'll have wires that are carried in currents, and they'll pull towards each other. If you measure that force, then I think, if I remember correctly, is the way that ampere was originally defined in terms of how much current creates a certain amount of force between two wires.
I have a question in the way that
Yeah, go ahead.
that maybe test exams are. So on the right-hand side, you have like the X part, which means the current is away from you or going through the screen, right? And then the left.
Yeah, those are the feathers of the arrow that are going into the screen.
Yes. And then the left side, it's the dot, which means it's coming towards you, which is why you were orientating your fingers towards you. Or, yes.
You were bending your fingers out of the screen.
Towards you. So is that how they'll depict it? Always?
Yeah, this symbol is quite standard. Okay. Circle with an X in it means in, and circle with a dot in it means out. It's like an arrow, right? These are the tail feathers of the arrow that's going into the screen, and this is the point of the arrow that's coming out of the screen.
Yeah, I just want to make sure that that would kind of be a way that they would ask.
Yeah, that's very, very standard notation. You'll see that a lot.
Okay, perfect.
Okay, let's talk about this situation. I always use up time. So, all right, I'm going to take a moment and take the attendance screenshot before I run out of time completely. So bear with me for a second. You can practice your right-hand rule. Okay, I have the attendance screenshots. I'll notate them later. Okay, am I back on the PowerPoint here?
Yes.
Okay, let's talk about this in the last few minutes. Okay, so now imagine that we have a magnetic, here's that notation again. We have a magnetic field that's coming out of the screen. Never mind where it comes from, it's just there, right? It could be created by magnets, it could be created by other things, but it's just there for our purposes. It's coming out of the screen, it's uniform, and now we have an electron in the plane of the screen moving towards the right. It's going to enter the region where the magnetic field is. So as a result, it will experience a force once it gets there. So let's figure out the direction of the force. Well, an electron moving to the right is a conventional current moving to the left. So straighten out your right hand and point your fingers towards the left. Now, spin your hand around so that your palm is facing outward. That way you can bend your fingers so that the fingers come out of the screen. Wait a minute. The other way. Excuse me. Rotate your hand so that the palm is facing towards the screen because the magnetic field is pointing in. I'm sorry if I misstated before. So X means that the magnetic field is pointing into the screen. All right, so let's start over. Electron that moves to the right is a current to the left. So pick up your right hand, put your fingers in the direction towards the left. Orient your hand so that the palm is facing the screen. That way, you can bend your fingers so that your fingers point into the screen in the direction of the magnetic field that's shown there.
So it moves down.
That's right. So which way is your thumb pointing? It should be pointing downwards. Right, the force experienced is down, at least initially. Okay. Everybody get that?
No. Can you do the one?
Again, I'm sorry, I have to just describe it in words.
That's fine.
I will wave with my hand, but ignore my picture. So take your flat hand and orient it so that your fingers are pointing to the left as you look at the screen. Right, that's the direction of the current. An electron, which is negatively charged, moving to the right, is a current moving to the left. So your fingers are pointing to the left. Now spin your hand around with your fingers always pointing to the left so that your palm is facing the screen. So you could put your palm directly on the screen. In that orientation, you'll see that you can bend your fingers so that they then point to the screen. That's the direction of the magnetic field. Magnetic field is into the screen. If you do that, you should have your thumb pointing downwards.
Okay, I'm with you.
Is everybody else with me?
Dr. Bretto, I'm sorry, I know we're running out of time, but why when the electron going to the right produces a current to the left?
By definition of what current is.
Okay, thank you.
The direction of a current is a direction in which a positive charge moves, or opposite the direction in which a negative charge moves.
Yes, I remember now. Perfect, thank you.
Okay. Okay, so initially when this electron enters this region, it'll feel a force downwards. And if you follow it around, its direction will change, and so the direction of the current will change, and it will curve around in a circle. Please ignore gravity. There's no gravity in this diagram. It's flying, and it'll go like this. So an interesting question is, what is this radius? Oh boy, I'm really out of time. All right, I will leave the slides, but on the slide, I try to calculate what this radius is, and I use these ingredients. This is the force experienced by the charged particle that's moving in a magnetic field. Our old friend F equals ma. Notice that it moves in a circle. So therefore, the centripetal acceleration is v squared over r. R is the radius. You can combine all of these to get this equation and solve it for the radius. There you go. That's the result of this slide. They can calculate what this radius is. It depends on the mass of the particle, the charge of the particle, and how fast it is. The faster the particle goes, the larger the radius will be. And I'm going to skip ahead for a moment and just point something out that's interesting. If you can figure out the amount of time it takes a particle to make a complete circle, if it's in space like this, the amount of time that it takes to make a circle does not depend on the radius. Here it is, the period. It only depends on the mass and the charge and the magnetic field. So if you have a slow electron, it'll make a small circle, but it'll take amount of time equal to t, say. And you have an electron that's going fast, it'll make a big circle, but it'll take just the same amount of time to make a circle as the slow-moving one with a smaller circle. So that's kind of an interesting thing. You'll hear the word cyclotron frequency. So the inverse of that period is this frequency, and that's cyclotron frequency. All right, I'm sorry, I'm out of time. I didn't get to go through my slides or the problems. I will post the rest of the slides. There are a couple ones here. I will post the questions that I had with my written solutions. But I know you guys have other classes to get to, so I have to now end class. I hope this was useful. I'll have an office hour tomorrow, Friday. Feel free to attend. I'll post the Zoom link in the announcement section of Blackboard. Again, I hope it was useful. All right, have a good weekend.
Always.
Everybody.
I'm sort of confused. It goes in a circle? Oh, let me read. I'll get back to you on a question tomorrow.
Well, I can hang around for a few minutes here. I'll put the slide back so I can point to it then.
Okay, yeah. If you can give me a brief, and then Julie had a question too on slide 17.
This one. You see it?
I do.
Okay, so initially when the particle moves into the field, we figured out that it experiences a force downward.
Yes.
Therefore, its path will be deflected. It is deflected as in the way shown. So take your hand and follow it around. Your hand would do this. See what I'm doing?
Yes.
So if you copy what I'm doing with your palm facing your screen, you'll see what's going on.
Okay. And it's because
so the motion of the electron is perpendicular to the direction of the magnetic field. In other words, it's in the plane of the screen.
Oh, I see. Because the magnetic field is making a loop anyway, so it's going to follow the loop as well.
No.
Oh, shnikes. Then
magnetic field is uniform and into the screen. What's happening is your hand is rotating around. The direction of the current is changing, so your direction of your hand has to change. The magnetic field is always into the screen, so the flat part of your hand, the palm of your hand, will always point towards the screen. But it will do this. Do you see me?
Yes.
right? As the direction of the current changes, you have to move your hand and keep your fingers in the direction of the current.
Oh,
And so you'll see the direction of the force has to also change.
okay. Okay.
So you're doing kind of a wax-on kind of maneuver onto the screen, if you know that movie reference.
I do reference. I do. I do.
Dr. Barreto, if this were oh my, the opposite of an
Go ahead.
electron is a
Proton.
proton. Oh my gosh, I'm sorry. So the current would be towards the right, correct?
Yep. And it would curve upwards.
But the force would still be downwards, right?
No, the force would be upwards. So if the particle were a positively charged particle moving to the right, put your fingers to the right, orient your palm so that it faces into the screen. That way you can bend your fingers into the screen where the magnetic field is. The thumb will point up.
Yes, I see. And then the curve would be towards the upwards too, you're saying.
Yeah.
Okay.
So it's a way of separating positive and negative charges. Right? You can throw them both in this direction. The positive ones will go up and the negative ones will go down. But again, when I say up and down, I just mean in that orientation because there's no gravity in this setup that I have on the screen.
And then Kirsten had a question. So the force makes the electron move downward. So as it moves downward, the current moves upward, and that continues on.
Yeah, basically, that's right. The direction of the current rotates. The direction of the force rotates as shown. That's right. Imagine putting your hand, your flat part of your hand on the screen and then kind of wiping it like this. Right, start with your fingers towards the left. And then, so don't look at my hand. Start with your fingers towards the left, putting your hand on the screen. And then follow the curve around and you'll see how the direction of the current changes and direction of the force changes.
That makes sense. Thank you. I was also wondering if the magnetic field were coming towards us, would the electron like make this circular motion moving upward?
Yeah, your hand would be flipped the other way. So the back of your hand points towards the screen.
Okay. Okay, thank you.
Because that way, if the magnetic field is pointing out, you want to be able to bend your fingers towards the direction out of the screen.
Okay, that makes sense.
So that's right. Good.
Wait, you were just saying that if it were coming towards us, then the force would be pointed up, correct? Is that what I?
Yeah, if the magnetic field were reversed and pointing outwards,
Yes, they were dots.
then this electron would feel a force upwards.
Okay. Thank you, Dr. Barreto. I was also wondering, you were saying how a positive charge goes into our chest away from the screen, and a negative charge, point charge goes.
Well, that was just describing this particular diagram.
Okay, is that something that's like a generality, or no?
No, particles can go in any direction.
Okay.
Do you see what's on the screen right now?
Yes.
Yeah, I was just describing this particular diagram.
Okay.
So that we could figure out how to do the right-hand rule.
That's great. Thank you, Dr. Barreto.
Okay, I got to go and set up the next recitations. I'll post an office hour, as I said, for Friday. Feel free to attend. And you're welcome. See you guys later. All right. Bye now. Oh, I'll stop the recording. Goodbye.